Okay, section 4.4, measuring motor position and velocity. This is from the Real-Time Computing for Mechanical Engineers book that I wrote with Garbini and Devine. I'm Dr. Piccone. MIT Press published the book. rtcbook.org is the companion website. Okay, motor position and velocity. Our design objectives in this book overall of controlling the position and velocity of the motor will require feedback, i.e., the measurement of the angular position or velocity of the motor shaft. This section reviews the primary methods of making such a measurement. The most common and useful class of sensor is the rotary encoder, a digital and usually optical device that is mounted on the end of a shaft, often at the rear of the motor. Here is what that looks like. A single channel encoder at left with a light source on the left-hand side, and on the right-hand side we have a photodiode or some other sensor for the light that is being emitted and passing through a slot in the rotor, which is attached to the motor shaft. When a slot is in between the light source and the sensor, light will pass through. When there is no slot in between the light source and the sensor, the light will be blocked and the sensor will not pick up any light. There are three common types of optical rotary encoder, shown at right. So here are the three. The single channel, right here, the quadrature, right here, and the absolute. The rotors of these three types are shown in the figure. So this is the rotor part, the part that turns around and is attached to the shaft. As shown in the figure at left, the rotor, which turns with the shaft, has evenly spaced slits on its periphery. So here are the slots, and we call the opposite of a slot a line. The encoder housing that encloses the rotor is often affixed to the motor frame. As shown in the figure on the previous slide, an optical source shines through the rotor slits and onto a sensor. The optical path is interrupted by the lines of the rotor. So when there's a line, the light does not shine through. When there's a slot, it does shine through. And so I have a line here that denotes the sense location. So this would be the location of a light source on one side and the sensor on the other side. Slits or lines are spaced at regular intervals such that each time the signal changes, a known amount of rotation has occurred. So we know how many degrees we've rotated when we see one blip of light and then a blank spot and then another blip. Okay, more about single channel encoders. The rotation of the rotor produces a series of pulses from the optical sensor. Assume that the shaft exclusively turns in one direction. If the initial position is known, the angular position can be inferred by counting pulses. Once again, we know how far it's turned each time we see a pulse. In practice, this technique is rarely used to track position because position is rarely important for a motor that rotates in a single direction. A single channel encoder is much more useful for speed measurement. Here, the relative displacement during a fixed time increment can be used to estimate speed. An encoder's counts per revolution, or CPR, specification is the number of lines per rotor revolution. Let us assume that sensed light corresponds to logical 1 and blocked light to logical 0. For a single channel encoder, there are two state changes per count. We go from a 1 to a 0 and a 0 to a 1. Therefore, for a single channel encoder with CPR C, each state change corresponds to a rotation R of 360 degrees divided by 2 times the counts per revolution. And the unit, of course, is in degrees. Okay, quadrature encoders. The quadrature encoder, shown at right, also called an incremental encoder, adds another optical sensor and digital output channels. Now we've got two sense lines, A and B. The second sensor and its channel, called B, is offset by 90 electrical degrees from the channel called A, as is illustrated in this figure. So this actually is very precise in terms of what the phase is of its difference. We could have so that when A is in the middle of a slit, so is B, but that would be 0 degrees of phase difference between them. We could have A in the center of a slit correspond to B being in the center of a line, and that would be 180 degrees different. But instead we have 90 degrees of phase difference in between them, and from this we'll be able to deduce the direction that the shaft is spinning. In the position shown, A equals 1 and B equals 1, so we have light shining through in both cases. If the next state is A, B equals 0, 1, so A is 0, B is 1, the rotor has turned counterclockwise. So if A suddenly goes dark, so it goes from 1 to 0, that means that we must have rotated this way, counterclockwise. Conversely, if the next state is A, B equals 1, 0, so A is still 1 and B is 0, we must have rotated this way so that A is still 1 and B is covered up by the line. The corresponding signals are shown in 4:16, which are these two figures here. So for counterclockwise rotation, which is this one, and for clockwise rotation, which is this one, we have these two figures. So this is the counterclockwise figure, and this is the clockwise figure. So if A leads B, the rotor is turning counterclockwise. This is a diagram that shows the trace over time, assuming that they're rotating at a constant velocity. We see that through time we have A leading B. So when A goes down, a little bit later in time, B goes down. When A goes up, a little later in time, B goes up. Okay, and so here is now shown where they're both positive, both 1 here. Conversely, if B leads A, meaning when B goes up, A goes up a little bit later, 90 degrees later, and conversely, when B goes down, A goes down 90 degrees later. So we can deduce, based on which signal is leading here, which direction the rotor is turning. There are 4 state changes per count for a quadrature encoder, so each state change corresponds to a rotation R of 360 degrees divided by 4c. The quadrature encoder is capable of measuring velocity, not just speed, and relative position. Velocity because it can determine the sign. If the initial position is known, the absolute position can be inferred using a quadrature encoder. Okay, and then the third type, the absolute encoder. Finally, the absolute encoder, shown here, typically adds even more bands of lines, but unlike those of the quadrature encoder, each band has a different line width. So we see each band, and the bands are radially spaced out here. Each band has a different line width. The furthest internal one has a line width that corresponds to just half of a turn each, and then there's more and more division as we go out. That's because there's more and more space. We wouldn't want to do it the other way. There's going to be a separate optical source sensor pair for each band. So we'll see a light source and a sensor for that light at each band here. So 8 channels shown in this figure. So as before, we can represent the state of each sensor with a 1 for light and a 0 for dark. So each band's state can be represented by a bit. The absolute encoder in the figure is 8-bit, but let us consider the n-bit encoder. Along the sense ray, each half line has a unique state for a total number of unique states 2 raised to the n power. The corresponding angular resolution is 360 degrees divided by 2 to the n. For the 8-bit encoder, the angular resolution is about 1.4 degrees. The pattern of the figure yields a binary representation that is not sequential. This version is called a gray code, which is popular, in part because only a single bit changes at each increment, which is quite nice, reducing the chance of errors due to slight band misalignments. So the gray code is a kind of a clever way of mitigating errors. Okay, we're going to take a look at an example encoder and some of its specifications. We briefly consider the performance and important design considerations for an example encoder. Given an encoder with 500 counts per revolution, 2,000 state changes per revolution will be produced. This results in an angular resolution of 360 divided by 4 times 500, or 0.18 degrees. The implications of these parameters must be carefully considered when using a quadrature encoder. For instance, if a computer's digital input can handle up to 100 kilohertz, this limits the maximum rotational velocity of this encoder to 120 kilo-RPM. The velocity can also be restricted by the electrical or mechanical limitations of the encoder. Due to the mechanical nature of the rotor, a maximum angular acceleration is often specified. For instance, consider an encoder with a maximum angular acceleration of 250 kiloradians per second squared. To check if this will be violated in a system design, the motor torque and load inertia can be used. Given a maximum motor torque of 2.82 Newton meters and a motor inertia of 56.5 times 10 to the 6 kilogram meters squared, the maximum acceleration is the quotient of the max torque divided by the motor inertia, which gives us 50 kiloradians per square second. This is much less than the encoder can handle, and of course, any additional load will greatly reduce the actual maximum acceleration. Okay, processing encoder signals. An encoder signal must be processed or decoded. Some encoders include a signal processor and others do not. There are also dedicated decoder ICs for quadrature encoders. A computer may include quadrature decoding functionality, and the main processor can also decode. However, a great deal of processing resources must be dedicated to ensure that no counts are dropped, so using the main processor is not always ideal. Encoder-based and dedicated IC-based decoders must also communicate processed data with a computer via a standard protocol such as Serial Peripheral Interface, SPI, or a buffered data bus. A single channel encoder has a single data channel, a quadrature encoder 2 or 3 channels, and an absolute encoder as many as n bits. The absolute encoder requires less signal processing because it is unnecessary to count state changes, but its high number of channels, 25 bits, is not uncommon, usually requires encoder-based decoding and communication. We briefly consider the commonly encountered design scenario in which a quadrature encoder without built-in signal processing must interface with a computer. So, processing quadrature encoder signals. An encoder quadrature signal can be processed by an intermediate device integrated into a microcontroller or system on a chip, SoC, or separately, as one or more dedicated ICs. Dedicated processors typically perform several tasks such as noise filtering, decoding, of course, counting, buffering, and communicating with the main processor. Some ICs, like the HCTL 20 series, include all these functionalities. Other ICs include only parts. For instance, the LS7083N filters and decodes, but requires separate ICs to count, buffer, and communicate. Communication to the main processor is typically via a buffered data bus. but protocols such as SPI are also seen. Communicated data includes the current counter value and the direction of rotation. A computer can process a quadrature encoder signal on its main processor, but the computational load can be problematic. Ideally, a computer includes dedicated decoding functionality. Without this, it is advisable in many cases to use a dedicated IC like the HCTL 2032. Programming the computer to use quadrature encoder data is highly specific to the hardware. We will see what this means for the T1 target system in the remainder of this section. So, programming the target computer encoder inputs. The MyRio, our target computer, has 4 quadrature encoder inputs, 1 on each of the connectors A and B, and 2 on connector C. Each has an A channel pin and a B channel pin. These are processed by the FPGA at up to 100 kilohertz. Pretty good rate. In this section, we will consider how to program the MyRio encoder inputs. There are 3 types of registers associated with each encoder input: a configuration register, a status register, and a counter value register. So first, the configuration register. Bit functionalities. Each of the 4 encoder inputs has a 1-byte configuration register that can be set programmatically. All register bits are 0 by default. Switching bit 4 to 1 and then back to 0 will clear all overflow flags in the associated status register. Switching bit 3 to 1 and then back to 0 will clear the error flag in the status register. Bit 2 is the signal mode. The default value 0 sets the encoder to quadrature encoding mode, and setting it to 1 enables step and direction mode, which indicates that one channel will carry timing information about steps and the other will carry direction information. We will use the quadrature mode. Setting bit 1 to 1 resets the corresponding encoder counter value register to 0, where it will remain until configuration bit 1 is set back to 0, at which point counting will begin again. So it's like a reset button that has to be released before it'll start counting again. Finally, setting configuration bit 0 to 1 enables the corresponding encoder, and setting it back to 0 disables the encoder. An encoder input can be configured with a MyRio encoder type variable. This type is defined in the MyRio C library's encoder header file. For instance, we can initialize a variable to configure encoder 0 on connector C with the following. So we declare a variable encc0 to be a MyRio encoder type. We assign the config, the stat, and the counter attributes to these values, which are defined in the MyRio 1900 header file. So this tells us this effectively sets C to be the connector and 0 to be the channel. Encoder C channel 0 to be the encoder configuration that we're setting with this variable. So now that we have this type all ready to go, configuration flags can be set using the encoder configure function from the library encoder.c source file and some bit masks. The encoder header file defines the encoder status mask and the encoder configure settings types. The encoder configure function prototype is this. So we have to give it the channel like we just configured, then we have to give it masks and the settings. So this determines which registers we're setting, and then this determines the actual settings. A configuration bit is selected with an encoder configure mask like encoder enable. The value to be assigned to the configuration bit is selected with an encoder configure settings type like encoder enabled. Multiple masks and settings can be combined with the bitwise OR operator. For instance, to continue the example here, by configuring encoder 0 on connector C to be enabled and in quadrature mode, use the following code. So this is the MyRio encoder type that we declared. We declared it to be the C0 encoder. So we passed that here, the address of that, as the first argument. Then we say these are the configuration bits we want to set. So encoder enable or encoder signal mode, which is to say these are the two settings we would like to set. We would like to set the enable bit and the signal mode bit. And then finally, the last argument, we want to pass enabled, which says set the enable bit to enabled. And then we also want to set the signal mode bit to encoder quad phase, so the quadrature encoding. Even if we plan on using a default configuration, it is best to explicitly set that configuration in any case. So this is what we will be doing in the lab. Okay, the status register. So we had the configuration register. We've finally finished. Now we're going to talk about the status register for a moment. The 1-byte status register for each encoder includes several overflow flags, an error flag, a direction bit that indicates the direction of the most recent change to the encoder counter value register. We can do an encoder status function call from the MyRio C library's encoder.c file to read the status of the register. So that one we won't dwell on too much. It's pretty straightforward. You can just ask it for the status and you can read the status back. Okay, finally, the last register, the register is actually for the counter values. These are the ones we're going to be using to actually read what are the counter values currently on the encoder. So we're going to consider the count the encoder has and how to get it. Each encoder input has an associated unsigned 32-bit integer counter value register to keep track of the count of the number of pulses we have registered from the encoder. In quadrature mode, if channel A leads channel B, the count is incremented. If channel B leads, the count is decremented. The counter can be treated as unsigned or signed. As unsigned, once the count reaches its maximum of 2 to the 32 minus 1, it overflows back to 0. If it is decrementing, once it reaches its minimum of 0, it underflows back to 2 to the 32 minus 1. The signed count works similarly, with its maximum of 2 to the 31 minus 1 and a minimum of negative 2 to the 31. When an overflow or underflow occurs, the corresponding bits in the status register are set, so we can discover if an overflow or an underflow has occurred. With an initialized encoder variable, like the one that we did in the previous slides, encoder C0, it is straightforward to get the current encoder count from the register with the encoder counter function from encoder.c. It's just given by encoder counter, and then you give it the encoder configuration. This will return the count, an unsigned specific width integer, unsigned 32-bit width integer, but it can be assigned and implicitly cast to another integer type, such as the signed int for our compiler, that is a 32-bit integer. So if we do an int cast, we'll get a 32-bit integer. Okay, so it'll give you the current count of the encoder. Okay, so another thing to consider here is how underflow and overflow work. From the difference between the current encoder count Ci and a previous count Ci minus 1 and the basic time interval, or BTI, the time that has elapsed between samples, we can estimate shaft position and velocity. So position from how many counts have gone by, and velocity by how much time each of those counts has taken. How will overflow and underflow affect estimates of position and velocity? Assume that the current and previous counts are represented by signed integer variables of width equal to that of the counter. For our C compiler, the int data type is 32 bits. Furthermore, assume that the angular position of the encoder changes less than 2 to the 32 over 2,000 revolutions, which is about 2 million, during a single BTI. That is, that the count is less than 2 to the 32. The difference is less than 2 to the 32. As a result of signed binary integer arithmetic, when we compute the difference between two integer types, the result is defined by the offset mod function. So the offset mod function here uses m, n, and d as its arguments. M is the value, n is the modulus, which we've seen before, d is the offset, and x with the brackets, the lower brackets on it, is the floor function. So this is the floor function, which means round down. Okay. The result is mod n, and always in the range from the offset to the offset plus n minus 1. For int data, the difference delta c is mod 2 to the 32, with offset d equals negative 2 to the 31. That is, delta c is mod ci minus ci minus 1, comma 2 to the 32 with an offset of negative 2 to the 31, which reduces to this formula here. Let's examine what happens at overflow. Suppose that the previous counter value, ci minus 1, was 2 to the 32 minus 2. So we're not quite to overflow, but we're going to overflow very quickly if we keep adding numbers. And during the BTI, basic time increment, the encoder has moved forward by 4. Okay, so 4 counts forward, such that the current reading is negative 2 to the 31 plus 1. So we've overflowed back to negative 2 to the 32, or sorry, negative 2 to the 31 plus 2. And the numerical difference between those two numbers is about 4.3 billion. However, applying equation 3, this offset mod, the 32-bit signed integer arithmetic, gives the correct result, where we put that large numerical difference number in, we mod it by 2 to the 32, and we have the offset of negative 2 to the 31. This equals 4. And it turns out that if you take a difference in the C programming language of these integer types, and there is an overflow, this offset mod function is actually what C implements. So you're not going to run into any problems when we take the difference here. You don't have to handle this manually. The C programming language is handling this difference for you, which is nice because it's a little bit complicated, right? Okay, so that is how to measure the angular position and velocity of a motor shaft using an encoder. Quadrature encoders in particular are what we've focused on. We've also seen single channel encoders and absolute encoders as well. We've seen how to implement the encoder count measurements programmatically in the MyRio. So, all right, we'll see you in the next section.